Hey everyone. Today we're going to talk about something we all think we understand, image resolution. You know, we've all been taught that more megapixels equals a better picture, but it turns out the real story of what makes an image truly sharp is, well, it's a lot more interesting than that.
So let's just ask it straight up. Is this equation true? I mean, it's the first thing we look for when we're buying a new phone or a camera, right? We check that megapixel count. The whole idea is the bigger the number, the better the picture. But is that really the whole story?
Well, the moment you step away from consumer cameras and into the really high-stakes world of advanced scientific imaging, like with X-rays, that simple idea just completely goes out the window. In this world, the search for true clarity is about so much more than just counting pixels.
And that really brings us to the heart of what we're talking about today. We have to draw a really sharp line between two different things: the digital grid that an image is built on and the actual physical detail that a system can capture in the real world.
Okay, so here are our two key players. On one side, you've got voxel size, that's the digital grid. And on the other, you have spatial resolution, that's what you can actually see. And let's be super clear about this, they are not the same thing, not even close.
So what exactly is voxel size? Well, think of it like a pixel, but for 3D. It's the tiniest little digital cube in a three-dimensional image. Its size just depends on the detector and how much you're zoomed in. But here's the key. It's just the box. It's the container for the information, not the information itself.
Now, spatial resolution, this is the real deal. This is what it's all about. It's the true measure of a system's power, its physical ability to actually tell two tiny objects apart when they're right next to each other. This is the real test of clarity. It's not about the digital box, it's about what the system can truly see.
And this quote just hits the nail on the head. Think about it. If you've got a blurry photo, right, and you decide to chop that blurry photo up into 1,000,000 tiny squares, it doesn't magically become sharp. All you've got now is 1,000,000 tiny blurry squares. You're just representing the blur in higher definition.
So, if having more voxels isn't the solution, what's the real enemy here? What's holding us back? Well, it turns out that every single imaging system in existence has this fundamental, built-in limitation. You can think of it as its own unique fingerprint of blur that it stamps onto every single image it creates.
This fingerprint, this is the true gatekeeper of resolution. It's a physical property of the system itself that sets a hard limit on the sharpest possible image it can never produce. And in science, this idea has a name. It's called the point spread function, or just PSF.
This is a great way to picture it. Okay, step one, imagine you have a perfect, impossibly tiny point of X-rays. In step two, that perfect point goes through your imaging system, the lenses, the detector, the whole shebang. But what comes out the other side is never a perfect point. It's always a little blurred out blob. And that blob you see in step three, that is the point spread function. It's the system's signature smudge. So here's the bottom line. The narrower and more focused that PSF blob is, the better the system's true resolution is, period. It's the real physical limit. If your system has a wide smeared out PSF, you're going to get a blurry image, and it doesn't matter how many millions of tiny voxels you try to capture it with.
All right, so if this built-in blur, this PSF, is the villain of our story, where does it actually come from? Let's take a look at all the different things that work together to create this unsharpness in the first place.
It's actually a fight on multiple fronts. You've got geometric unsharpness, which is basically a shadow effect from the X-ray source itself. Then the detector adds its own blur, maybe from energy bleeding between sensors, kind of like sound bleeding through a wall. Of course, any little vibration or movement causes motion blur, just like in a regular camera. And believe it or not, even the software that puts the 3D image together can add its own kind of blur too.
But this isn't a story about giving up. No way. This is a story about incredible creativity. Because faced with all these physical limits, scientists and engineers are on this constant quest for clarity, and they're coming up with some brilliant ways to fight back against the blur.
And they're really waging this war on two main fronts. On one side, they're building better, more precise hardware, and on the other, they're writing incredibly clever software that can computationally cut right through that haze.
And the hardware advances are just incredible. I mean, take these new liquid metal jet X-ray sources. They use a constantly renewing jet of liquid metal, so they can be pushed way harder, achieving up to 27 times higher brightness than the old tech. 27 times! That is a total game changer for getting a sharp, powerful signal. So let's look at the modern toolkit. For hardware, you've got amazing things like photon counting detectors, which capture data with just ridiculous precision and way less noise. But the software side, man, that's where a revolution is happening. You've got deconvolution algorithms that can literally look at the system's blur and then mathematically undo it. There's iterative reconstruction, which uses massive computing power to build cleaner images from the start. And of course, AI and deep learning are now being used to intelligently clean up noise and pull out details you'd never see otherwise.
So, what does this all add up to as we look to the future? We've gone from this very simple myth about megapixels all the way to this complex and fascinating reality of physical limits and brilliant computational workarounds.
The biggest takeaway from all of this is pretty simple. Getting to true, meaningful resolution, it's not a numbers game. It's not about counting pixels. It's about understanding, measuring, and ultimately winning the physical fight against blur by using smarter hardware and even smarter software.
Every single one of these advancements gives us a clearer, more powerful window into these invisible worlds. Worlds hidden inside materials, inside our bodies, inside our technology. And that just leaves us with one final and really exciting question. As our scientific vision gets sharper and clearer, what new worlds are we going to discover next?